Hello everyone, I am Dr. Sirajul Faisi. I welcome you in my YouTube channel. Today in this video, I am going to talk about crystalline solid state. You already know about the many molecules which exist in the solid state. So we will focus on crystalline solid composed of atoms or ions. So friends, one thing keep in your minds and eager to learn about the unit cell. What is the unit cell? You know, a structural component that when repeated in all directions results in a macroscopic crystal. So 14 possible crystal structure, Bravis lattice, and discuss positions of atoms in the unit cell. Now friends, the cubic unit cell or primitive, one atom per unit cell. What is the coordination number? Volume occupied. Let's calculate the length of the edge. What size of a sphere would fit into the hole? Now friend, the body centered cubic. How many atoms per unit cell? What is the length of the edge? This is a more complicated system than the simple cubic. Now friends, close packed structure. What is this? The question is, how many atoms is each atom surrounded by in the same plane? What is the coordination number? Hexagonal close packing, SCP. Discuss the third layer, ABA. Cubic close packing or face centered cubic, FCC. Discuss the third layer, ABC. Two tetrahedral holes and one octahedral hole per atom. Can you see them? So friends, the SCP has hexagonal prism sharing vertical faces. How many atoms per unit cell in the SCP structure? What is the length of the cell edge? The unit cell for the CCP or FCC is the harder to see. Need 4 close packed layers to complete the cube. What is the length of the cell edge? In both the close packed structure, 74.1% of the total volume is occupied. Now friends, what is the ionic crystals? The tetrahedral and octahedral holes can have varying occupancies. Holes are generally filled by smaller ions. Tetrahedral holes, octahedral holes, sodium chloride structure. Now friends, metallic crystals, most crystallize in BCC, CCP and SCP structures. Hard sphere model does not work well, depends on the electronic structure, properties, conductivity and dislocations. What is the diamond? Each carbon atom is bonded tetrahedrally to 4 nearest neighbors, essentially the same strength in all directions. Structures of binary compounds. Close packed structure are generally defined by the large ions, usually anions. The positively charged ions occupy the holes Friend, two important factors in considering the structure: radius ratio R plus divided by R minus. R plus is always up and R minus is always down. Relative number of combining cation and anions. Now you can see here the sodium chloride crystal structure. Face centered cubes of both ions offset by a unit cell in one direction. Many alkali metals have this same geometry. And what is the coordinations number? Nearest neighbors. You can see here cesium chloride as crystal structure. Chloride ions form simple cubes with cesium ions in the center. The cesium ion is able to fit into center hole and other crystal structure. Now titanium oxide, the rutile structure, distorted titanium O6 octahedra. Titanium has a coordination number of 6 octahedral coordinations. Oxygen has a coordination number 3. Now friend, rationalization of structure of crystalline solid. Predicting coordination number from radius ratio R plus divided by R minus. A hard sphere treatment of the ions treats bonding as purely ionic. Simply as the M plus ratio increases, more anions can pack around it. Let's look at a few examples: sodium chloride, calcium fluoride and calcium chloride. Now friend, thermodynamics of ionic crystal formations. A compound tends to adopt the crystal structure corresponding to the lowest Gibbs energy, M plus in gas plus X minus gas, it gives Mx solid. Del G is equal to del H minus T del S, standard state. Second term can be ignored. Lattice enthalpy, standard molar enthalpy change. Currently we are interested in lattice formations. You can see the Born-Haber cycle, a special thermodynamic cycle that includes lattice formations as one step. The cycle has to sum up to 0 if written appropriately. Write down the values for potassium chloride. The Born-Haber cycle calculate the lattice enthalpy for magnesium bromide. A discrepancy between this value and the real value may indicate the degree of covalent character. We have assumed Coulombic interactions between ions. The actual values for potassium chloride and magnesium bromide are 701 and 2406 kilojoule per mole. Now friend, lattice enthalpy calculations. Considering only Coulombic contributions, the electrostatic potential energy between each pair, del U is equal to ZA ZB divided by R naught, E square divided by 4 pi epsilon 0. Here ZA and ZB ionic charges in electron units, R naught distance between ion centers, E electronic charge, 4 pi epsilon 0 is permittivity of a vacuum, E square divided by 4 pi epsilon 0 is equal to 2.307 into 10 to the minus 28 gm. Calculations would be performed on each cation anion pair nearest neighbor. A more accurate equation depicts the Coulombic interactions over the entire crystals. Del U is equal to Na E square divided by 4 pi epsilon 0 square under bracket Za Zb divided by R naught A. Here capital Na Avogadro's constants, A Madelung's constant, value is specific to a crystal type in table given in the book. This is the sum of all geometry factors carries out until the interactions between infinitesimals. So repulsions between ions in close proximity term del U is equal to Na C epsilon minus R naught by rho. C is equal to constant will cancel out when finding the minimum. Density is compressibility constant. Combining term del U is equal to Na E square divided by 4 pi epsilon 0 Za Zb R naught A plus Na C prime epsilon minus R naught by rho. Lattice enthalpy calculations finding the minimum energy minus du divided by dr naught is equal to 0. Del U is equal to Na Za Zb E square divided by 4 pi epsilon 0 R0 1 minus rho by R naught A. A negative of this value may be defined as the lattice enthalpy. You can see here lattice spacing, repulsion, attractions, potential energy. Lattice enthalpy calculations as the polarizability of the resultant ions increase the agreement with this ionic model worsens. Polarizability generally indicates more covalent character. Calculations sodium chloride and calcium bromide. You can see the molecular orbitals in solid, most antibonding and most bonding, intermediate orbitals. A very large number of atoms are used to generate molecular orbitals. One-dimensional model, creation of bands that are closely spaced, factor affecting the width of the band. This would be called an S-band. A similar model can be constructed for the p orbital and d orbitals. So the bonding picture in the solid, most antibonding and most bonding. Now band gap separations between bands in which no molecular orbital exists. So valence band, highest energy band containing electrons. Conduction band, the band immediately above the valence band in energy. So metal partially filled valence band, S band. Electrons move to slightly higher energy levels by applying a small voltage. Electrons and holes are both free to move in the metals. Overlapping bands, S and P bands. If the bands are close enough in energy or overlapping, an applied voltage can cause the electrons to jump into the next band, conduction band. Density of states, concentration of energy levels within a band, d by d in energy. You can see d small area and p in S band, density of states. It helps to describe bonding reactivity in solids. Conductivity of solid versus temperature. Metals decrease with temperature, semiconductor increase with temperature, insulator increase with temperature if measurable. Semiconductor types, you can see the donor band and acceptor bands. Intrinsic semiconductors, pure materials having semiconductive properties. Doped semiconductor, semiconductor that are fabricated by the adding a small amount of another elements with energy level close to the pure state materials, N-type semiconductor and P-type semiconductor. So Fermi level,